Hi everyone, today we are going to see about artificial neural networks in machine learning. A neural network that consists of hidden layers with a neuron. So a single neuron is mapped into a set of inputs into an output number. Here it can be mapped with r to the power k to r. So a1, a2, ak that represents the input, w1, w2, wk that represents the weight. So summation, then a bias is added, we can get the output as z. So activation function is used, it is represented by sigma of z. So the final output is a. Single neuron maps a set of inputs into an output number. A neural network with one hidden layer and one output layer. Okay, here the input is represented by x, hidden layer is represented by h, and output layer is represented by y. Okay, so for hidden layer, that h is equal to sigma of w1 into x plus b1. So that b1 b2 represent the biases, w1 w2 represents the weights. Okay, that sigma that represents the activation function. Here actually this the total number of nodes in hidden layer and output that represents the total neurons. So 4 plus 2, 6 neurons are there. Here how we have to calculate the weight is, here 3, here it is 4. So 3 into 4 plus 4 into 2. Okay, totally 20 weight representation. So 3 into 4 plus 4 into 2. Okay, input to hidden, hidden to output. So total 20 weights, and bias is calculated from 4 plus 2. Okay, so totally that weight plus bias that represents the learnable parameters. So this is a simple example for a deep neural network which consists of many hidden layers. You can see the input as 1. Okay, so the weight that is also 1. So minus 2. So 1 into 1 plus minus 1 into minus 2 plus this bias 1. Okay, so the output is 4. The sigmoid function is calculated by 1 divided by 1 plus e to the power of minus 4. So the answer is 0.98. So similarly for this one also we are calculating the sigmoid function as 0.12. So here it is represented in a vector form. So we are getting 0.98, 0.12. Then after processing in another 2 more layers, we can get the final output as 0.62 and 0.83. So this is the input vector 1 minus 1, and we are getting 0.62, 0.83. So this is how we are representing in a function f of 1 minus 1, that is equal to 0.62, 0.83. Multi-dimensional input and output is representing. So sigma of this w that represents the weight function. So this is the input function 1 minus 1, and this is the bias function 1 and 0. Okay, so sigmoid of all these values that is given by the final output 0.98, 0.12. So this is with multi-dimensional inputs and output. Multi-layer neural network. So matrix calculation for the first layer. So inputs are from 1 to up to n. So n number of inputs are there. So we are calculating the matrix for the first layer. So the input is x, weight matrix is w1, bias vector is b1, and output vector is a1. So this is how the matrix is calculated for the first layer. So this is for all the layers, that a1, a2 up to y. Here for this multi-layer neural network, the function f that maps the input x to output y. So that y equal to f of x. So this is how the process is done. So softmax layer. So in case of a multi-class classification task, the output layer is typically a softmax layer. It generally employs a softmax activation function. If a layer with the sigmoid activation function is used as a output layer, Instead, the prediction by the neural network may not be easy to interpret. So here the softmax layer applies softmax activation to output a probability value in the range of 0 and 1. The values Z inputted to the softmax layer are referred to as logits. Here you can see the activation functions. The nonlinear activations are needed to learn the complex data, which means the nonlinear data. Otherwise, the neural network would be just a linear function. Sometimes a neural network with a large number of layers can approximate more complex function. It may overfit. So next one is activation of sigmoid. So here it takes a real valued number and squashes it into the range between 0 and 1. The output can be interpreted as the firing rate of a biological neuron. Not firing is denoted as 0 and fully firing is denoted as 1. So when the neurons activations are 0 or 1, the sigmoid neurons saturate. The sigmoid activations are less common in modern neural networks. Here that f of x that is defined by 1 divided by 1 plus e power minus x. And the next activation is tan h. Here it takes a real valued number and squashes it in the range between minus 1 and 1. So like sigmoid function, tan h neurons saturate actually. But unlike sigmoid, here the output is zero centered. It is therefore preferred than sigmoid. So this tan h is a scaled sigmoid and it is represented by tan h of x that is equal to 2 into sigma of 2x minus 1. And the next one is rectified linear unit. It takes a real valued number and thresholds it at 0. So that f of x that is defined by maximum of 0 comma x. So most modern deep neural networks that use this type of activation because it is very fast to compute compared to the previous activations sigmoid and tan h, and also it is simply threshold a matrix at 0. It accelerates the convergence of gradient descent and it prevents the gradient vanishing problem. So when x is less than 0, that f of x is 0, and when x is greater than or equal to 0, it is represented by x. The final one is leaky rectified linear unit. Problem of the previous activation rectified linear unit is overcome by this method. Actually, that rectified linear unit causes weights to update in a way that the gradients can become 0 and the neuron will not activate again on any data. A simple example is when a large learning rate is used. So, but here in this leaky rectified linear unit, instead of function being 0 when x is less than 0, a leaky rectified linear unit has a small negative slope. This resolves the previous issue, and most current works they still using the rectified linear unit with the proper setting of learning rate. And the linear function, so here that output signal is proportional to input signal of the neuron. If the value of the constant c is 1, it is called as identity activation function. This activation type is used in regression problems. So then training a neural network. Here training a model to learn a set of parameters that are optimal is a main challenge in this machine learning. So here we are giving an input as 16 cross 16 image. So we are having 256 pixels that is represented as inputs from x1 x2 up to x256. So we are using a softmax layer before the output layer to train a neural network. So data pre-processing, it helps convergence during training, and that means subtraction that is used to obtain zero centered data that subtract the mean for each individual data dimension, that is a feature. So then normalization means it divide each feature by its standard deviation. So to obtain the standard deviation of 1 for each dimension, or scale the data within the range of 0 to 1 or minus 1 to 1. A simple example is that image pixel intensities are divided by 255 to be scaled in 0 to 1 range. Define a loss function, we otherwise is called as cost function. So we have to define that L of theta that calculates the error between predicted model and true label. So that is represented by L of theta. So loss function is calculated on both the classification task and regression task. In classification, they calculated as crash entropy. During the regression, it can be calculated as mean square error and mean absolute error. So learning rate, an important thing. So the learning rate is that the gradient tells us the direction in which the loss has the steepest rate of increase. Choosing the learning rate, which we call as step size, is one of the most important hyperparameter settings for a neural network. If it is too small or too large, both of them causes some slight changes in the output. Either we are having a high learning rate or low learning rate. So when the learning rate is high means the loss increases. When the learning rate is low means the loss decreases too slowly. That depends upon the epochs we chosen. So generalization, here two concepts are there: underfitting and overfitting. That underfitting that produces a high error on the training set and validation set. It is a model with very few parameters. This underfitting, that is too simple to represent, and overfitting is that it is a model with many parameters. Actually, it produces low error on the training set and high error on the validation set. Overfitting model is too complex and it causes more noise in the input data. And this is a regularization. So for every weight in the network, we add regularization term to the loss value. So during the gradient descent parameter update, every weight is decayed linearly towards 0. So here this lambda that determines how dominant the regularization is during the gradient computation. So batch normalization that acts similar to data processing steps that mentioned earlier, that calculates the mean, mu and variance sigma of a batch of input data and normalize the data x to a zero mean and unit variance. It is calculated by x cap, that is equal to x minus mu divided by sigma. It allows a large learning rate and it results in faster convergence training, and it reduces the internal covariant shift, and they are very common with convolution neural networks. The final one is that hyperparameter tuning. So that includes the total number of layers and neurons per the layer. Then the learning rate that we initiated, then the optimize the type that we are using. So apart from this, the remaining parameters are regularization parameters, batch size, the activation functions, cost function, etc. So this tuning can be a time consuming for large type neural networks. So we can meet in the next video. Till then, goodbye from Vijay. Thank you.